This is the interim presentation for Design for Manufacturing about the analysis and redesign of a stapler by Team 5.
Our selected product is a standard manual desk stapler. It fastens paper by using a spring-loaded lever to drive a metal staple through the sheets. Typically uses an injection molded plastic housing, stamped sheet metal parts, spring, pins, and rubber feet. We chose it because it has 10 to 20 components. It is mass produced at about 200 million units per year, and it uses course-related processes like injection molding, sheet metal fabrication, machining, and assembly. The primary customer group is everyday office and school users, such as students, teachers, and businesses who need a low-cost, reliable, easy-to-use stapler. The secondary customer group is high-volume professional users, such as legal offices or departments that staple more frequently, where durability, comfort, and staple capacity matter more. Here's the exploded CAD view showing each component. As you can see, the stapler we are working with specifically has 14 total components. Next is our functional analysis. As you can see, the single main function for which the product is to ultimately fasten papers. It is what the product is for. The next level over is the primary basic functions, as well as the predefined categories. And then for each function, there are two or more functives that directly answer how does the product perform the function. We ended up having 14 total of these. And as you can see with the diagram, as you move from left to right, it always answers how. And as you move from right to left, it answers why.
For our first assembly sequence, we proposed a modular build. The stapler is split into three sub-assemblies: base, top arm, and magazine, each built in parallel at its own station. All three then meet at the final mate step where the pivot pin joins them into the finished stapler. Our second sequence is a linear build, everything assembled at a single station, one part at a time. We start with the base frame and stack upward through the pivot pin, driver arm, magazine internals, and finally the top housing. No sub-assemblies, just one growing stack. To choose between them, we scored both against five criteria. Modular wins on handling because sub-assemblies stay rigid while the linear stack grows tall and awkward. It also wins on locating parts since each station works against clean fixtures rather than accumulating tolerance up the stack. Fastening is a tie because both use the same joints. Modular wins on testing because each subassembly can be verified before integration, while linear can only be tested at the very end. And modular wins on parallel assembly. The three stations versus one is a decisive mode for production speed at 200 million units per year. Based on the final score, we selected modular for the bill of materials and DFA work that follows.
This is the function component matrix. You can see by the chart that it is pretty well balanced. All components have several functions, at least more than two, and no single function needs over 40% of the total components.
For our bill of materials, the cost to produce a stapler is about $1.24 per stapler. This was found by totaling material cost, assembly cost, and tooling cost per part for all parts. Material cost was found using CAD mass and industry standard rates, assembly cost from the 5-digit codes in class, and average U.S. labor rate of $25 an hour. Finally, we found the tooling cost from approximate volume and equations from lecture. For the quad chart, cost cutoff was decided at 8 cents. Functional importance was decided based on relevance to task performance. From this, we can see that the upper cover and rubber base pad show room for improvement with their high cost and low functional importance.
Now we're going to discuss the product family design. We start off with the functional differentiation chart. After comparing the functions on the FAST diagram with our primary and secondary customers, we identify 4 functions that need to be different. That being prevent slip, improve appearance, improve grip, and reduce effort. That being because the secondary group is for a targeted group that uses the stapler much more.
Moving on to the component commonality, the modules that address the different customer groups are the top plastic housing and the rubber base pad, as they can change to match aesthetic, ease of use, and maneuverability, while also giving more ergonomic value to each user, depending on whether the shape and the size of both the top plastic housing and the rubber base pad. The first module is the top plastic housing. The interface that deals with is the upper metal frame, which connects to the top plastic housing to the rest of the stapler. The second interface is the base frame, which deals with the rubber base pad. It will deal with either grip pads or plug-in pads, depending on whether the stapler wants a full grip pad or a small little plug-in pad.
In order to optimize large-scale production, it is important to delay differentiation to reduce potential waste. This is done through a product family assembly diagram, which branches only when necessary with two varieties of the top housing, base pad, and final assembly. Thank you.